is by the winner of the best dissertation of icaps 2009, DanBryce. And the title of the talk is Reachability Heuristics for Scaling Planning Under Uncertainty.
Thank you. I'd like to take this opportunity, since I just graduated, to provide some advice to some of the students out there. So I want to give you an idea of the 5 worst times to give a conference talk. This is actually a slide I used on my very first icaps conference talk. So it was on the last day. It was on the last session of the last day. It was the last talk of the last session of the last day. It was the last talk after the Best Paper Award. And yours was the winner of the Best Paper Award on the same topic. So now I've kind of graduated, and I've changed it to the best time to give a conference talk, where essentially you end up where it's not the last talk, the last session, the last day, and you're actually getting an award for it. So I'd like to start off by thanking some of the people involved in actually getting me through my PhD. First off is Rao, my advisor. And then also my PhD committee, which was comprised of David Smith, David Musliner, Chita Baral, and Goran Kanjan. And also the Yochin Research Group during the time that I was at ASU. Mankus, Will, Jay, Terry, Min, Romeo, Satish, and Samwook. And all of the sponsors that I had during that time. And also all of you, because from all the interactions I've had with you over all the icaps I've been to, it helped me along the way in one way or another. So I'd like to start off by presenting, kind of a motivation for why I did this dissertation. Is I came to Rao and I said, well, I'm kind of interested in planning under uncertainty. I don't really know what I want to do, but it sounds like a cool topic. And actually I found out that handling uncertainty is a pretty important problem. And the example that I gave in my defense was that the Mars Pathfinder mission, they spent $265 million at the time, and it was wasting 40 to 70% of its time just doing nothing. And the reason it was doing nothing was because of plan failure. And a lot of the reasons you have plan failure is that you have all kinds of uncertainty about your environment. So I'm listing 5 things here. The first 2 that are the ones that I'll actually be concentrating on is having incomplete information and imperfect actions. So what you can do in these scenarios is either replan, you come up with a plan that's going to break, you fix it somehow, or you pre-plan. You either come up with a conformant or a conditional plan. And where I'm going to be focusing is on the pre-planning aspect of how you actually scale up the synthesis of conditional and conformant plans. So just kind of as a primer to the kind of models we'll be looking at is on the y-axis here I'm showing the problems in terms of the observability that you may have, and then along the top is the kind of uncertainty you may have about the environment, whether it's qualitative or quantitative. So I developed a planner called Pond. You might have seen mentioned in a few papers. It does conformant, probabilistic, and non-deterministic planning, which would be those 2 squares on the left, and then it does conditional probabilistic and conditional or conformant probabilistic planning. So just to give you an idea of how hard these problems are, this is a search space for a conformant non-deterministic problem. Well, when you're given an instance, you're going to have on the order of p state variables, and then obviously that means you're going to have 2 power p states, and then you're going to have 2 power p belief states. So in the worst case, your search space is going to contain a doubly exponential number of nodes. Now there's various ways of making this nice, but I'm not going to be focusing on that aspect of it. It's the heuristic aspect of exploring the space that is my interest. So to give you a synopsis of the dissertation is, we're looking at this as a search problem. We said, okay, classical planning heuristics are pretty good. Why don't we look at those and see how we can extend them to do useful things for us? But I'm kind of nowadays not so sure if classical planning heuristics are the answer. There's kind of come up in this conference that there's a whole lot of other things that I need to consider as well. So if I ever go back for a second dissertation, I'm going to add in some things to Pond to do that. So the question was really, can we have classical planning heuristics adapted to do planning under uncertainty? And the obvious answer is yes, else I wouldn't be here having a dissertation. And kind of the subtitle to this talk is I want to underscore the fact that implementation details do matter when you're solving these types of problems. And it's not just that you have a heuristic, it's that you have a heuristic you can compute in an efficient way. especially because we're dealing with these double exponential size spaces. And also, can we ever beat York? And when I say implementation details, this is not the type of implementation details I'm talking about. I've anonymized the innocent and the guilty, but I've shown my planner here being shown as just basically crashing on every instance of the domain. So this is not the type of implementation detail I'm going to be concerned with. Okay, so coming back to classical planning, really the thing that's changed classical planning over the past, I don't know, I've heard the term pre-95, or rather 95 time frame, things have changed considerably. And this is kind of the state of the art before that time, where we were scaling exponentially on the rockets problem, trying to get 8 packages to the moon. Nowadays, this is from the 2004 IPC, this is the results for the airports domain, where we have planners routinely solving very large plans with hundreds of actions. And kind of one of the key insights to this is reachability heuristics, where what the idea is you have a state and you do a relaxed projection into the future in order to estimate the reachability of the goals from each of those states. And from that, you compute a heuristic. So, to kind of give you an intuition for why this makes sense, if we have a search space like this in front of us, where this is the state space that's been expanded, if we have a planning graph, the literals that appear in the level of the planning graph are an overestimation of the literals that would be reachable in the states at a certain depth in the search space. So as you can see, planning graph is a kind of an approximate form of logical inference where we're trying to estimate the literals that are reachable as opposed to the states that are reachable. Okay, so I'll be talking about 4 chapters of my dissertation. There's actually 8 chapters, and I'm not going to talk about all of them. So the first one is really, what is the foundation under which we're computing these heuristics? So imagine we have 2 belief states here on the left, and we have a belief state here on the right. What we're trying to do is compute the distance between these dark lines. So if I were to have a classical planning heuristic in front of me, I would be able to compute the distance from each one of these states in the belief state to one of the goal states. But the problem is, how do I aggregate these individual costs that I've computed using a classical planning heuristic? Now, it's not really clear which ones I should choose as being the best node to expand in order to reach this belief state on the right. So, because I have these individual numbers, there's various different ways I can aggregate them. And the intuition we use is generalizing the notion of aggregation of achieving of sub-goals in classical planning to aggregating the costs of states in planning under uncertainty. Okay, so in classical planning, you can aggregate the cost of sub-goals like using the maximum cost, which would give you a full assumption of full positive interaction. Or you can do summation, which assumes that all the plans to achieve the sub-goals are independent. Or you can do a relaxed plan, which is like something kind of in between the two. So for planning under uncertainty, we can do the same sorts of things by aggregating the measures for the states. So the first thing we might do is just create an approximate state and compute a classical planning heuristic just from that approximate state, where we take the union of all the literals in all of the states. Turns out to not work so well. The other thing we can do is we can compute a heuristic for each of the states, take the maximum of those, which would assume full positive interaction among all those states trying to achieve the goal. Then we can also take sum, where we'd be making the same assumption, where achieving the goal from each of the states is independent. And one of the first heuristics I came up with that was fairly effective and actually become, I guess the term has been coined a conformant relaxed plan, and it's also shown up in some other works, is where you're accounting for both positive interaction and the independence of the states in the ways in which they achieve the goal. So you're looking at the overlap, the shared actions that they use. So to give you an intuition for what this union heuristic is, so if I was just going to compute a heuristic for this belief state here on the left, I would compute a planning graph for each one of the states. I would find the goal reachable, and I could extract like a relaxed plan for each of one of these planning graphs. Now, I'm still at a point where I need to aggregate each of these methods. So I could take the sum and I would get something like 8. Take the max, I would get 3. But the union relaxed plan, what it does is it looks at each level and tries to find actions in common among the same levels. So in a sense, it's sharing that action, because I only really need to do that action once in a conformant planning problem. So here I would only count 1 to this level because the same action is used in each of these different states. In these other levels I get 3 and 3, so I get a heuristic of 7 here. Okay, so this is the heuristic is actually in between what I would get if I used max or sum. So I'm counting for the positive interaction. But turns out this is costly. Our belief states can be exponential size. Computing an exponential number of planning graphs is not a good idea. A naive approach, what you might say is just, okay, I'll sample a subset of the states, compute the planning graphs for those, and aggregate them in that way. And I'll show you results to show you why that's not necessarily a good idea. Actually, having a better representation is the right approach. Before I do that, though, I'll give you an indication of how effective these heuristics are. So what I've shown is several instances along the bottom here. They're separated by this column here. And each of these heuristics, what I'm showing is, one is the ratio of the heuristic estimate from the initial state in the problem to the optimal heuristic, or the optimal plan length for the problem. Now, the heuristics I'm showing that I want you to pay attention to is the MRP, which is taking the maximum of the relaxed plans of all these planning graphs, the SRP, which is taking the sum, the RPU, which is actually taking this union thing I just described. And as you can notice, that the max is always going to be lower than the actual distance. So the ratio would be below 1. So in all these places, the square is below 1, which you would expect. Then the sum, which is the crosses here, is generally above. In certain cases, it's below because it's ignoring some negative interactions in the problem that would make it greater. But the union heuristic is typically in between the two, and it's often very close to 1. So it is a good estimator in these domains. Okay, so moving on, then I've established that the heuristic is actually a pretty effective or accurate heuristic. I want to focus on how to actually compute it efficiently. So the intuition we had is that if we look at this graph, each of these graphs shares a lot of common edges and nodes with the other graphs. So why don't we just take the union of them? If we take the union of them, then we could just compute a heuristic off of this. But we're missing something still. What I'm missing is, I don't know what parts of this graph is relevant to which of these states. So what we came up with is a mechanism which we call the labeled planning graph, or LUG, or labeled uncertainty graph, where what we do is we make each of these states a propositional model. So states are already propositional models. And then we associate with each of the nodes in the planning graph a label, which is a propositional sentence whose models correspond to the states that reach that particular node. So if you look at one of these nodes, it would actually be a propositional sentence of this kind of form, where we have some disjunction because there'd be 3 models of it. I'm actually using inclusive OR here, but it should be an exclusive OR. You get the idea. So we came up with a way to propagate these labels across this planning graph. And what you do is, if you're looking for a way, in conformal planning, you're looking for a way to achieve a goal from every single state. So you do this until your goal here is labeled by each one of those models. Okay, so from there, you can actually directly extract a relaxed plan from this graph without having to extract a bunch of graphs and then aggregate them somehow. So the idea is that when you have a goal and it's reached by some set of models, you try to pick actions such that the set of models that the actions contribute covers the models that you need to support the goal in. So here we choose this action here. We pick each one of these models in order to support the goal. It has a precondition, and it is supported by individual different actions from different models. So these are from different states. And I've labeled them as such. Then each of these guys, I have to support their preconditions. The thing that I wanted to point out, though, about when I'm supporting the preconditions to some of these actions, their preconditions may be reachable at many of these states, but I only really need to support some of them from the states in which they're used to support other actions that are leading to the goal. Okay? I'll come back to this point later. It's very compact, but subtext here is we have to compute this for every single search node. I thought I had a half hour. Okay. So to give you an idea of how this works is, if I were to sample states from my belief state in order to compute heuristic, building each one of the planning graphs by themselves, I would actually be doing a little bit better if I only sample 10% of them. But as I sample more states, I actually have to do more work. But if I use this label approach, the more states that I use, the better. Because what I'm showing here is the total time to solve all the problems in a test suite. That total time actually goes down when I use this labeling approach. So I'm actually not losing any information, and I'm actually getting better runtime because I've implemented the heuristic in a more efficient way. Okay, so we set this idea to search in probabilistic belief states, and instead of York, we're dealing with Carmel now. And the idea is that we have distributions over states and actions with probabilistic effects. So if we were to do this in a kind of extending the style of the conformal planning graph, what you have to do is you have to start branching over the uncertain outcomes of actions and creating proposition layers for each of the outcomes of these actions, which is typically a very bad idea. But the idea here, if we were to do this, it would be an exact probabilistic inference over an approximate logical inference, which doesn't quite make sense. So instead, what we did is we used Monte Carlo, and we would sample the action outcomes at each level of the graph and figure out which of those samples actually lead to proposition layers where the goals are achieved. From there, we can get an estimate of what the probability of achieving the goal is at every level of the graph. But we already know how to do a labeled graph, so we want to do this for the Monte Carlo graph. So the way this is done is we decide how many samples we want to take for the Monte Carlo, and then we draw samples from our belief state and associate a sample with each of those states. And then we create the first proposition layer, labeling each of the literals with the samples in which it was generated. Then we do the same sort of propagation as before. The new thing about it that we're doing here is, say for example, we have this action here. It's reachable by two worlds, but its effect is only given in one because we've sampled its effect. So this is the new thing that's happening in the graph when we have probabilistic effects. We just sample the outcomes and propagate those samples in that way. So it turns out that we compared this to the state of the art at the time, which was CP Plan by Fahim Backus. And he had shown that, on this grid world problem where you have this robot that goes in the wrong direction with some small probability that he's doing about this good. He can solve the problem with about like 0.01 probability. And then using our approach, we're able to solve the problem with up to 0.95 probability. And plan lengths here are, on the orders of 100 of actions. Then we made the problem more stochastic, and we basically showed that if the problem's more stochastic, you need more samples in order to get a good heuristic. Okay, so how much time do I have? 0? 2? Okay. The last approach is called the state agnostic planning graph, where what we did is we identified that in classical planning, we're building planning graphs for each of these states, and the planning graphs are more or less the same. So we have the same sort of problem that we had with conformal planning. So what we did is we said, okay, well, let's build a labeled uncertainty graph for all the states. And we can propagate the labels over this thing. And eventually we get our goal achieved by all this label here, which is entailed by several different propositional models. And those are exactly the states in which the goal is reachable. So what this does is it's representing every single planning graph I need in order to compute a heuristic. All I need to do is extract the heuristic from this. So I'm not going to go into detail how to do that. But to show you that there are certain cases in classical planning where using this approach works better than the planning graph. So this is just a XY plot of the performance on some domains where the SAG is actually better, or that using a planning graph where you computed every single node is better. And then this is the speed up factor. So generally, as the problems get harder, the speed up factor is greater. So we came up with a version of this called the state agnostic lug, where we want to use the same thing for non-deterministic planning. Now, use basically the same graph, but we have to extract it for several of the models instead of just one, which we would do in classical planning. So actually here, using the slug, it basically dominates using the planning graph because we pre-computed. We're actually using this graph quite a bit more than we would in classical planning because belief states share states. So we would be using the graph for those states over and over and over again. And the speed up factor is actually considerably greater even as the problem increases. So here's some results. We entered this in the planning competition. It did okay. That's about it. Then we've extended this to the Monte Carlo slug, where we've done the same sort of thing where we use determinization of actions. This is extending the lug to be state agnostic, so we compute all possible planning graphs for a probabilistic planning problem prior to even doing search. Looks something like this. The neat thing that I haven't published yet, it's in a forthcoming journal paper, is called a SAG relaxed plan, where what we do is we can extract every single relaxed plan you would ever need prior to search. And it's just a simple lookup in order to do model checking to figure out if your state uses one of those actions in the relaxed plan. So if you're interested, let me know. Okay, so here's some results comparing this approach to PFF, where this is some domain that was used by CPPlan. All of these techniques tend to outscale CPPlan in this, or PFF in this problem. Here's some domains that PFF guys came up with. This is the state agnostic relaxed plan I just mentioned. It's actually required in order to scale up in these domains. So they're only finding plans around 10% probability of success, and we're finding ones that are closer to 0.6, I guess. So considerable difference. Okay, so I'm done. Summary. So I did belief state distance heuristics. The SAG is kind of like a planning graph pattern database, and the SAG relaxed plans are kind of like a relaxed plan pattern database. Okay, and that's it. Thanks.
Okay. With a piece of work, just one question about the relation between distance among beliefs and distance among stage. So all your heuristics seem to me you're making the assumption that you can derive the distance among beliefs as an aggregation of the distance among states.
Right.
But distance among beliefs cannot be reduced to distance among states. So it's a very strong assumption. Okay? So you can get the state distance of one and belief distance of infinity at the same time. So have you thought about the fact that in general this reduction is strong? Okay, and may give very weak estimates.
Well, in general, we found that it's the strongest estimator out there. The other approaches have been actually additional relaxations on top of this, that in some domains they actually scale a lot better because of that extra relaxation. So, yeah, you're right. We are missing the fact that the distance is actually infinity. In order to do that, you might have to do a stronger negative interaction propagation like doing mudexes. Doing that involves going back to the CGP literature and trying to understand cross-world mudexes and that sort of fun stuff. So
that's not the dimension I have in mind. It's the fact that you're not only supposed to reach the goal in these programs, you're supposed to know that you have reached the goal. So this epistemic component is what is missing when you reason from states. Okay, the epistemic component is not a matter of reaching the goal. You're supposed to know that you reached the goal. So if the goal is here and you don't know whether you're here or here, so in one case you have to move right, the other one move left, and the grid is infinite. So the belief state distance is going to be infinite. Okay, even though you are a distance one from the goal.
right. So this would show up in problems like mastermind and so forth, where you have to know the goal. And in the benchmarks that we've looked at, it's typically just achieving a set of ground literals, and it's not a problem.
Another question? So we now can conclude this section, but before doing so, I would like to remind you that the awards will be given later this afternoon during the icaps community meeting. So thank you again.
Can I make one last comment before you end?
Okay.
So I was expecting a question from Rao, which he asked all of the people that get this award. Well, what am I doing now? So I'm actually not working at Google. I'm working at Utah State University, and I've been doing work on a project called Bootstrap Learning. So ask me about it if you get a chance. Thanks.